I've got about 10 questions here from the May 2022 Time Zone 2 Paper 1 that one of your colleagues has found tough, and he's asked me to give a little bit of guidance on. So hopefully this is useful to more than just him. The first question is around working out the order for increasing ionisation energy, and you might remember that as you go across any period, such as period 3, which these elements are all in, the general trend of ionisation energy is increasing, and that's because you've got the same number of shells overall, and you've got an increasing number of protons, so there's a greater attraction between the protons and the outermost electron, and so more energy is required to remove it. But there's a couple of minor points you need to remember, that as you go across a period, the trend is increase from group 1 to group 2, then there's a little drop, we'll talk about the reasons why in a second, and then it goes up, and there's a little drop, and it goes up again. You need to know that sequence, all right? So this would be sodium, magnesium, aluminium, and so on and so on, like that. Okay, so the drop here is due to the fact that the outermost electron for magnesium is being taken from a 3s orbital, whereas the electron that's the outermost electron from aluminium has been taken from a 3p orbital. Now, 3p orbitals are higher energy than 3s orbitals, and so this requires less energy to remove. Remember that if you imagine an energy level diagram like that, to remove an electron means taking the electron from, say, there's a 3s orbital, if you like, and there's a 3p orbital. Less energy is required to remove an electron from a 3p orbital than it is the 3s orbital. So it's ever so slightly easier to remove this one. And then it comes back up again as you get more protons. It drops here again. And I'm not going to answer that now, but just look at the, make sure you know the reason for that. This is all to do with, very briefly, I'm going to do it then, 3p2, 3p3. This is 3p4, and for the fourth electron is sharing an orbital. The electron that's removed is sharing an orbital with another electron, so there's a little bit of repulsion there between those two electrons, so that electron is lost more easily. Okay, that's that one. Right, so question 17 is about delta G, because delta H minus T delta S. This is really a derivation from delta S total, which is the entropy change that's for a reaction in total, is equal to the entropy change of the system, which is what we know is called delta S, and entropy change of the surroundings, which is the when a chemical reaction happens, if it's exothermic, say, heat is transferred to the surroundings, the universe, if you like, and the universe will have a bit more entropy because it's heated up a little bit, right? So higher temperature, and so that measure there, so this derivation. So I'd look up, if you want to look at this in detail, look at the derivation of delta G from delta S total equation, and delta H is equal to delta. It's that. You're not going to be asked to derive this equation, but you probably should know that delta H is a measure of the change of the entropy of the surroundings, because they would change in entropy if heat is transferred to them, and heat being transferred to them is going to come from the fact there's an enthalpy change in the reaction, i.e. delta H, which is why B is the answer. Question 19 is a tricky one, it's a little sneaky one. This is almost a trick question, right? So I think why people might get confused with that question, I'm just going to get a slightly clean bit of paper there, is that you're asked about the loss, the rate of disappearance of one of the reactants. You're given the rate equation, which is rate is equal to K times H2 concentration times the concentration of NO squared. So in the rate determining step, or before the rate determining step, you've got NO twice and HO once. So it'd be very tempting to assume that NO is being lost faster than H2. But of course, that's just the mechanism of reaction. All of the steps in the mechanism are happening. It's just that one step happens to be the rate determining step. So I reckon the rate equation might look something, you'd have to work this out, but the rate equation might look something like this. So step 1 might be a fast reaction between NO and NO to make N2O2, so that'll probably be fast. And the rate determining step, which would be step 2, would be this N2O2 reacting with H2, which is slow. Right, so before the rate determining step, you've got that and that and that. That might give you, say, H2O plus N2O. This is just a suggestion. I don't know whether this is right or not. And step 3 would be something like N2O reacting with the other molecule of H2 to give you H2O and N2. That seems to make sense to me. Fast again. So all of these reactions are taking place, and during the course of the reaction, of course, you look at the balanced equation, NO and H2, they're both being lost. They're going to be lost at the same rate as each other in total, because you've got 2 moles of NO reacting with 2 moles of H2. They must both disappear. At the end of the reaction, they've all gone, haven't they? So it has to be that. Hopefully that's clear enough. It's not about the rate at this point only. You've got to take into account that the H2 will be lost in a very fast step immediately as soon as this forms. Right, question 20. You are expected to simply know the shape for SM1 energy profile diagrams, and it actually makes sense if you think about it. So you should know that for SM1 there's a transition state, and that transition state gives you this well in the energy profile diagram. The question was that the student raised is why C and not D? Well, if you think about it, the transition state, if I draw it down here, for SM1 might be something like that. We've got a carbocation in this SM1 reaction, so chlorine, say, has been lost, or chloride's been lost, so you end up with that. But the second stage of that reaction, the first stage is losing that chlorine, which is going to take a lot of energy. The second stage is the hydroxide then attacking it. Well, it kind of makes sense that that process, that's going to have a pretty low activation energy, because no bonds are being broken in that second stage. So that's why it's C and not D. Again, I think question 24 is kind of awkward. You should know that ammonia is a weak base. If you have a quick read of it before I go through it, pause it and have a read of it. But you should know that ammonia is a weak base. Reacts with water. You get a small amount. This equilibrium weight lies way to the left. You get ammonium ions and hydroxide ions, which is why ammonia is slightly basic in pH, as pH in water has a pH slightly above 7. So if you add water to the ammonia, this equilibrium is going to shift to the right a bit. Okay, so you're going to get more hydroxide ions in solution if you add water to it. You're just shifting the equilibrium to the right. Okay, so this number goes up. That's why that increases there. But you're adding water to a very dilute solution already, and it's just going to get more dilute. You're adding lots of water to it. Yes, the number's going to go up a tiny bit because it's an equilibrium shifting to the right, but you're swamping it with water, which is going to actually decrease the concentration overall, because it's how much there is dissolved per decimeter cubed of water. Right? Question 27. What can act as both Lewis and Bronsted-Lowry bases? So Lewis acids are lone pair donors, so anything that's got a lone pair. So anything with a minus charge will have a lone pair. So the hydroxide, of course, does. Cyanide does, and ammonia does. They're all Lewis acids. And which ones can be Lewis? Bronsted-Lowry bases, they're things that accept H+, so they can all react with H+ to form the acids. Weak acid is just neutralization of water, and you know that H+ will react with this base as well to make NH4+. In fact, anything that's a Bronsted-Lowry base will be a Lewis base as well. 31, I don't need to do, part of the old spec. Question 39, anything to do with quantitative electrolysis, which is what this is, you can just ignore. Question 39 was actually not that straight, not that difficult. I didn't think. You've been told you add sulfuric acid to barium hydroxide, you get precipitated barium sulfate. So you're told everything you need here. The clue is barium sulfate that's a precipitate. A sulfuric acid is hydrogen ions and sulfate ions in a pot, and barium hydroxide is barium ions and hydroxide ions. So ionic solutions, of course, conduct electricity. And at the start, you've got barium hydroxide in the pot, right? One of those and two of those. That's going to conduct because ionic solutions conduct. But if you add sulfuric acid to it, this reaction takes place and you end up with a solid ionic compound that doesn't conduct. And you've got you're going to use up eventually all of the sulfuric acid. Sorry, you're going to use up all of the barium hydroxide with the sulfuric acid that you're adding. Now, if you kept on adding the sulfuric acid, you would of course start to get more produced in the end, like we got for C there. But in this one, you've got the same number of centimeters cubed and concentration of sulfuric acid and barium hydroxide, a 1-to-1 ratio they're reacting in, right? So that's why it's B and not C. Lastly, which is the strongest acid? Well, this is an acid because it's losing a proton before it turns into its conjugate base. This is a base, it will turn into its conjugate acid. So the acids are this one, and this one. It had to be one of those. That was the answer. You might have just seen that I paused the video there and checked it because I realised what the answer was. I'd circled C, but D is, I'll just check them asking D is the right answer. So I was heading in the right direction with it. For some reason I circled C there. Yeah, so this is an acid because it gives away a proton to make its conjugate base. This is a base to make its conjugate acid. Right, so which of the acids is the stronger? That one or that one? It has to be one of those two. Now this equilibrium constant, you know that Kc is equal to concentration of H3O plus times H2AsO4 minus over the reactants water and H3AsO4. That equilibrium is lying way to the left hand side because this number is tiny, and that means that these are the denominator is really big. The denominator is really big. It's telling you that equilibrium lies to the left, so that must be the stronger acid. This must be a very weak acid, otherwise that number Ka would be very big. That's it. I hope that's useful.